All right, hey guys, and welcome back to another AP Physics C video. Today we're going to be deriving the electric potential of a uniform rod of charge that is a distance d away from a point P. And it's going to look just like this diagram that I have up here. But in this instance, if you watch the last video, this is going to be negative lambda instead of a positive q. So we're not given a charge, but we are given a length and we are given a charge density, negative lambda. We're not given anything else besides the distance, the length, and the charge density. And like I said in the last video, we're going to treat this like a rod of charge or a line of charge. And it doesn't matter that it's a cylinder because we're not given radius, so we don't have to care about that. We don't have to care about like any Gaussian cylinder or anything like that. No, we're just going to treat it like a line of charge. So let's just jump right into it. Like last time, we're going to visualize a little dx, right? That corresponds to a little dq. And like last time, we're going to establish this as our 0 point, right? And we're going to visualize, well, how far away is that dx from that 0 point? That would be our r, right? Slash, and I'm going to call this slash x. So x is the distance we are away from the point P, or r would be the distance we are away from the point B. It's really the same thing. I'm just choosing to use x because I want lambda to be dq dx. So we'll get to that later. But basically, as you can see here, that dx, again, it's so small that it can be treated like a little point. It's infinitely small. So if it's so small, it can be treated like a little point and it has charge dq, it can be treated as a point charge. And we know that the electric potential from a point charge is k q over r. So if I think about now here, there's a little dv contributed at that point by that dq. The little dv from that little point charge, dq, is k dq over r. Now, say I wanted to get the total contribution. The total contribution would be if I summed up on both sides, right? If I summed up using an integral, because the integral, if you haven't learned in calculus already, it's an infinite sum of little small pieces d. So if I have integral dl, that just sums up little dl's, that'll give me L, right? Same thing here. So I'll sum up all the little dv's, that'll give me v slash, or v total, whatever you want to call it, is equal to k integral dq over r. But now we want to think, well, what dq's are we summing up from where to where? Because we do need bounds of integration to complete this. So we have to think, well, from where to where am I going to sum up these little dq's from? And like last time, if you saw the video, we know that we encounter the first dq at x equals d, and the next dq we're going to encounter at x equals L plus d. And the reason why it's d and L plus d is because we want to consider, if I think about this little dq, that's like right here, well, that dq is only a distance d away from the point P, right? Whereas this dq might be a different distance, like d plus some random number. That would be this contribution. So we're going to call that x, right? So now we're going to do that variable swap because x is varying for all of those dq's. And if you saw last video, you know I put a r hat here for electric field, but we're not going to do that this time because voltage or electric potential is a scalar. It doesn't have direction. It isn't a vector, right? So now I have this equation, k dq over x. And if you might be able to tell, you might be thinking, okay, well, 1 over x is varying for each little dq, but I can't integrate 1 over x with dq. I need to have a dx in there in order to actually integrate it. So this is where lambda comes in. We know that the charge density is negative lambda, but by definition, lambda is equal to dq, that's really bad, dq dx. So negative lambda dx is equal to dq. And this is starting to look a lot like rotational inertia. Just dq is dm, right? Well, dm would be dq, right? So now we're going to take that fact and we're going to sub that into our integral. And, oh, I think I forgot to do the bounds of integration. I'll do that right now. So now we have this integral, and our bounds of integration, like I said, they start from d, and they go to L plus d, and I explained the reason for that is because dq, or that rod, the dq's start at x equals d, and they end at x equals L plus d, because that's how long the rod is, that's how far away the little dq's will be from the rod, right? So we can just make that our bounds of integration. So now I'll just pull out my constants, negative k lambda, d L plus d, 1 over x dx. And now, if you know the integral of 1 over x is actually ln x. And that's going to vary from d to L plus D. Now we're going to get negative k lambda, and we're going to do ln L plus D minus ln D, because that's how calculus works. And now I'll get negative k lambda. And we're going to use our property of logs, that if you subtract two logs, that's basically, you can consolidate them by dividing the left one by the right. So if I have ln A minus ln B, that is equal to ln A divided by B, so long as B is not equal to 0, right? So I'm going to use that rule. I just did that here. That's the same thing, right? So now, oh, I think that's my final derived equation. Here we go. So yeah, that's pretty much it. That is your electric potential at that point. And I hope this helped you guys in any form that, well, you needed help. And if you guys have any more questions, please feel free to put them in the comments. But if you're also thinking, well, will they ever give us a lambda that's like negative lambda naught x is equal to lambda as a function of x? Usually the answer is no, because it'll require a complicated integral that will require u sub. Like u sub is not complicated, but sometimes it might be an integral that requires, like, I don't know, like a calculus 3 approach or a calculus 4 approach even, or like a transform. You won't have to worry about that. Usually they'll just give you a constant lambda. So yeah, I hope this helped you guys, and I hope you guys understand it a little better now. So see you guys in the next video.